Hello, logic people. Back in my garage.
Don't I sound super excited?
Time for some more logic. Time for some truth tables. Okay, we're at our third and hopefully final installment about truth tables. Today we're going to focus on truth tables and validity. Remember what validity is? Okay, given the truth of the premises, the conclusion is guaranteed, not 90%, not 95%, not even 99%, 100% guaranteed to be true. Okay? We also talked about this applies only to deductive arguments. Why? Because inductive arguments are not intended to guarantee the truth of the conclusion. So the standard of good form, validity, right? Well, the standard that inductive arguments use is not even the standard of validity. It's the standard of strength, as we've talked about before. Validity then applies only to deductive arguments. What's a deductive argument? That's when the author intends to guarantee the truth of the conclusion on the basis of the premises. Okay, intends to. All right, let's look at how to determine the validity of arguments using truth tables. Let's first of all take an argument form even that we know to be valid. Let's take modus tollens. Remember what that is? Okay, we've been using geometrical figures, circle, arrow, square, not square, therefore not circle. You deny the consequent, which leads to a denial of the antecedent. That makes sense because the consequent functions as a necessary condition. So if you don't have the necessary condition, if the necessary condition doesn't obtain, that's the second premise right here, then the antecedent here doesn't obtain. It is false. So we know that this is valid, modus tollens. We're going to use statement letters because that's what we've been using in truth tables. Okay? But that expresses the same form. Now what we're going to do in a truth table is to write up the argument in one line. In one line. Okay? Write the argument. That's to be tested in one line. So that's going to look like this. P arrow Q. And then what we're going to do is a comma. We're going to separate the premises using commas. Not Q. And then we can use a symbol for therefore. I'm going to use the 3 dots. Okay, like that, to symbolize therefore. And then you have the conclusion here, not P. So this right here, the argument written on a single line is called a sequent. Definitely learning new words when you learn logic, right? So a sequent. So sometimes I'll say write down the sequent, or sometimes I'll say write down the argument. A sequent is just an argument written in one line. Okay? I'm going to erase this side of the board and truth table this argument in sequent form. All right, let's truth table modus tollens. All right, put the sequent on the upper right of your truth table. P arrow Q, not Q, therefore not P. Okay? Upper right, like this. What letters are you going to put right here? Do you remember? P, Q. 2 letters, how many rows? 4. All right, then what you do next is just truth table all the columns right here, or all the main columns at least. So you're going to truth table the column underneath this arrow, because that's the main operator for P arrow Q. You're going to truth table underneath the tilde here, right? That's the negation of Q. You want to determine the truth values there. Fairly straightforward, right? And then you want to truth table the column underneath the tilde here for not P, right? So you're going to get 3 columns here of truth tables. Just do that mechanically. Then we're going to interpret it, all right? So let's do this here. Okay, which rows are true, which rows are false? If you remember how to truth table a conditional, it would look like this. Given these rows, we're going to get TT, FT. Not Q, okay, you just negate the values here, FF, TT. Notice how I always put it underneath the relevant operator. I don't put it in the middle or under Q, right here. I'm kind of pretending in a way, I'm imagining that this row, there are, right? There are letters under here. There's T's and F's under Q right there. I'm imagining it's there. Also, I'm telling the reader that this column directly applies to that tilde, okay? And it applies to this right here. All right, try to keep it as clean as I can. Not P, right here, you're going to get F, T, F, T. All right, you can imagine the P right there, T, F, T, F. All right, so the truth tabling is done here. The truth tabling is done. Okay, but that's not the end of the story. You have to interpret, right, to try to figure out whether the argument is valid. Okay, now you have to interpret. The table to determine validity. What you do here, what you should do here, is look for a row. There are 4 rows, so go through the rows. Look for a row where the premises are all true. Okay? They turn out to be true, but the conclusion false. Is there a world, in other words, where the premises don't guarantee the conclusion? Is there a possibility? Okay? Row 1, no, the premises are not both true. You have a T and an F right there. Actually, that tells us nothing about validity. All right? Go through the premises here. TF, TF, FT. The only one that really concerns us is this situation. In row 4, where P is false and Q is false, the premises P or Q and not Q turn out to be true. So here we have a world where the premises are in fact true. Okay? Does it guarantee a truth? Or does it lead to a truth? Yeah, it leads to a truth. Is there a situation where the premises are true yet lead to a false conclusion? No. No. There isn't such a row. So this argument is valid. It's valid. Now I just spoke through, I'll write it up in a little bit. But before I write up the method of how to determine validity, let's truth table an invalid argument. And what we're going to do is we're going to kind of tweak modus tollens to make it a fallacy. Let's, instead of denying the consequent, let's deny the antecedent and see if we can prove that, right, that argument to be invalid. Okay, so we have begin with P arrow Q, comma. Now the next premise is instead of not Q, it's going to be not P. And the conclusion will be not Q. Okay, so let's test this argument for validity. The left-hand side is going to look exactly the same because you still just have two letters, P and Q. All right, P arrow Q. There we go. That's done. Not P, FT, FT. Not Q, F, F, T, T. I'm going to pause for a second. Do you see how that works? Make sure I didn't, commit any typos here or something like that. Everything appropriate there, everything work? We've just truth tabled this sequent, this argument form here. Actually, we sequented, I guess you could say sequenced or something, the infamous fallacy of denying the antecedent. Okay. All right, now let's determine validity. Is it valid? Is this sequent here valid or invalid? Okay, so what we do is we look for a row where the premises are all true, yet the conclusion false. Here we didn't find such a row, therefore it's valid. Okay? Will we find a row here? We should, because we think, don't we, that it's invalid. Let's prove it though. Row 1, the premises are not both true. Row 2, look at row 2 here. Here's a situation where the premises are both true, yet we have a false conclusion. This row demonstrates, proves invalidity. Or you could say that this argument form here, denying the antecedent, is invalid. Actually, any argument of this form, circle, arrow, square, not circle, therefore not square, is invalid. The premises, the truth of the premises, do not guarantee the truth of the conclusion. Okay, what I'm going to do next is kind of write down the method for determining validity or invalidity, right, using truth tables. Okay, regarding truth tables and validity, this is what you need to know. A symbolic argument, that's what we've been doing. We've been symbolizing these arguments. We've been calling them sequence when we test them. A symbolic argument is valid if and only if no row of the truth table makes the premise formulas all true. If there's one premise formula, right, is it true? If there's 20 premise formulas, are they all true? But the conclusion false. Okay, that's what you're looking for. Let's do another example from the book. Okay, remember your book? This. Hopefully you have it. You've been reading it. That kind of thing. Introduction to Logic by Richard Arthur. Okay, let's do this one. This argument has two premises and negation as the conclusion here. Okay, so the first premise, L arrow M. Okay, let's separate it with a comma. M arrow not L, and the conclusion is not L. Okay, upper right of your truth table. There's only two statement letters involved here, L and M, so 4 rows. Okay, over here, T, T, F, T. M arrow not L, let's put in the not L here. F, T, F, T. Okay, M. I'm going to put that in just so you can see this a little bit better. Okay, so this one's done, this first premise. The second premise, let's do this. Let's see, row 1. What is the value right here, T or F? Should get fast at this. This would be a false. T, T, T. Notice that? Antecedent is false, you're going to automatically get a true right here. The conclusion formula, let's see, F, T, F, T. Now what you look for is a row of the truth table that makes all the premise formulas all true, but the conclusion false. If you find such a row, okay, if you find such a row, squeaky, the argument is, what is it? Invalid. Okay? Might be a little bit odd in a way if you successfully find it, it's invalid. Lack of success means it's valid. All right? That's similar to the counterexample technique. If you can't find a counterexample, then the argument's valid. Okay. If you can't find such a row, okay, then the argument is valid. Okay, let's go back to this one. Row 1, let's see. That premise formula is true, that premise formula is false. So now this doesn't tell you anything. Premise formulas, okay. True, true, yay. True conclusion. By the way, that too doesn't tell you anything, because an invalid argument, as we've seen before, can have true premises and a true conclusion. So the fact that you have such a row like this, T, 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 does not make it valid. The only test is this one, no other test. All right. Okay. Third row, FT, so don't even look at that's not even relevant at all. Okay, so the first 3 rows don't tell us anything here. Fourth row here, true premise here. Okay, all the premise formulas are true. Conclusion, it's true. So the argument is valid. There is no row where the premises are all true and the conclusion false. So this is valid. All right. Okay. Does that make sense? Okay, let's go back to this argument here. I'm going to tweak something a little bit. All right. So this argument had the conclusion not L. I'm going to take the negation sign off here. Let's make that conclusion L. So that's going to change the truth values in this final column here. In other words, what I'm trying to do is see if I can make this invalid. So now it's L as the conclusion. What we're going to get is T, F, T, F. Now let's go through the rows. Okay. I'm going to actually take these off. They drop out in a sense. They're not needed. So let's just look at these. First row, you don't have all true premises, so it's irrelevant. Second row now, look at this. Premises are both true, conclusion false. The fourth row too, premises true, conclusion false. So by taking the negation sign off of the conclusion, I've made this argument invalid. Invalid. Okay? I don't know. Frowny face, I don't know, whatever. Okay. Just made that argument invalid. All right. This is kind of a transition move to what's called the brief truth table method. That's what the book calls it here. The brief truth table method. Sometimes it's called the shortcut method or backwards technique method. So this is what we're going to do. We're going to look at the same sequence here, rewrite it, but instead of creating a full truth table with 4 rows, we're going to see if we can actually create a truth table. We're still using the truth table method in a sense, but it's not with 4 rows. The point of it is this: to try to create a row where the premises are all true, the conclusion false. We're going to try to make that happen. Instead of creating a full truth table and then going through all the rows, 8, 16, 32 rows, and trying to find that row, if there are any such rows, where the premises are all true, the conclusion false, why not just try to make it? If we can make it, then we've just proven that the argument's invalid. If we cannot create such a row, right, consistently, where the truth values are consistent, then we have a valid argument. So let's try to do this. Often, when we use this brief truth table method, we start backwards. We start with the conclusion. The conclusion has to be false. If we want to create that row, if we want to create rows 2 or 4, see this? Create those rows. We know we need to have a false conclusion. So let's just start like that. Now, we want to make each premise true. Okay, so let's start with this first premise here. How do we make this true? Well, there's a couple of possibilities, right? To make this true, L could be true and M could be true. Okay? So that'll make the first premise true. So let's try that right there. Well, if M is true here, it's got to be true here. You need a consistent set of values here. L, okay, true right there. So not L would be false. Look, we cannot make this one true, given L and M are true. So this particular, we not create a row under this scenario where L is true and M is true. So let's try a different combination. Another way to make L arrow M true is to have L false and M true. So that'll make this premise true. Will it make this premise true? Okay, so M is true here to match this, right? There's this value. Okay, let's try this one on. This one didn't work. Let's try this one. L is now false, so not L would be true. True antecedent, true consequent, true. Okay, we just created a row where premises are all true, conclusion false. This would be row 2 of a full truth table. And look, there it is. We just created this row right here. TTF. We created this way. Now this one took us 2 rows to create. That's still faster than 4 rows. Brief truth table method. Okay. Let's look at another example. And I don't want to. Let's not pick a. Let's see. Let's not pick a very difficult one yet. We'll get to that. Let's do one here from the book. This is exercise 18 on page 211. L arrow M. And the conclusion is M or L. Okay. So let's put that in the upper right. Begins the same way as the full truth table method. Over here we have L and M. But instead of writing down all the truth value combinations, we're just going to work one row at a time, really. Okay, it generally works well in a brief truth table method to start from the conclusion. Let's make the conclusion false. Make that false. Now to make this conclusion false, M or L, what does M have to be? What does L have to be? We know the answer. M has to be false, L has to be false. Let's plug those values in over here. Okay, L and M are false. Now let's see if we can make, if this conclusion turns out to be true. Okay, false, false, that's true. What we've done, we've created right away a row where the premises are all true and the conclusion false. So the argument is, we have success here in a sense. We found consistent values here. It is invalid. Again, it's kind of odd. For successful, it's invalid. If we're unsuccessful, or if we create an inconsistent set of values, it will be valid. You see this? This is invalid. If you created a full truth table, this would have been row, you can get right, row 4. I'm going to do a little bit of erasing, and we're going to use the brief truth table method on something a little trickier. Okay. Remember the liar paradox that we talked about earlier in the semester? We talked about the Star Trek version of it. It goes like this. Captain Kirk says this to Mr. Spock. With regard to, was it a prisoner or something? I don't know. He says that he's lying, but if he says he is lying and he is lying, then he isn't lying. However, if he says he is lying and he is not lying, then he is lying. Thus, he is lying if and only if he is not lying. All right? What we're going to do, we're going to check this for validity. Now, if you remember this example from earlier, we saw that it actually is valid. Doesn't mean it's sound, but it's valid. Let's prove that it's valid using a truth table. Or if you're not sure, like, I think it's invalid, we could check that. All right, let's write it down in sequent form here. What do we have here? We have, he says that he's lying. Let's call that S. So that's the first premise. But if he says that he is lying, and he is lying, I want to make sure I have room here. Let's do it like this. Let's put it over here. We're gonna have S and L. Those are going to be our letters. Okay, so S. If he says he's lying and he is lying, then what do we have here? Then he's not lying, not L. Okay, third premise. If he says he's lying and he's not lying, if he says he's lying and he's not lying, then he is lying. Therefore, what is it? He's lying if and only if he's not lying. Okay? So here's the way we begin this truth table. Now you could just do the 4 rows. That's not too much of a problem. And you could just do that mechanically. But let's try to do the brief truth table method. This is a good example for kind of testing our skills in making such truth table work. All right, so what we're going to try to do is this. We need all the premises to be true. So you can actually begin this way. You can say S has to be true. S has to be true. By the way, that is totally forced. We can't, there's no other possibility for S. All right. This premise here also has to be true right here. S and L, arrow, not L. That whole premise has got to be true. So underneath the arrow, which is the main operator, that's got to be true. So we're going to try to make that premise true. We're going to try to make this premise true. We're going to put the T underneath the main operator there, the arrow. That is a conditional statement. Okay? The conclusion, what we're trying to do is trying to force the conclusion or make the conclusion false. Remember, that's how the brief truth table method works, to to be false. Okay. To make this false, all right. Well, there's two different options here, but let's try one. Okay. L being true. L being true. Okay. And if L is true, then not L is false. That's not a problem right there. Easy. No matter what value you plug in for L, right, this biconditional will turn out to be false. So that's not a problem. Okay? If L is true, then this biconditional is false. So far, so good. Okay? Let's start plugging in values and see if we can make a consistent set of values such that all the premise formulas are true, the conclusion false. If that's the case, then it is determined to be invalid. Let's see if that works. S is true here, L is true here, right here, taken here. This whole thing is true. L right here is true, so not L would be false. Ouch. Nope. Can't do it. Can't do it. But we're not done. There's another possibility. We can make the conclusion false by having L false. Right here. Now S has to be true, so we just leave that there. S has to be true, no matter what. So we still have that true premise there. We have the false right there, that's great. Okay, let's see if we can make this premise true. Okay, well if L is false, not L would be true. By the way, conditional is always true when the consequent is true. So no matter what we get here, this will be true. But we can fill it in just for for completion's sake here. Let's see, just to be make sure we get everything covered. False antecedent, true consequent, we get our true premise. Awesome. What about over here? Let's try to make that conditional statement true. Well, L is false right there, so, okay, we can make this true as long as S and not L is false. Okay, so S, true, not L, true, okay, now we have this conjunction true, we can't make that work. So, under both possibilities, where L is true, L is false, we cannot come up with a consistent set of values across the board. So, what have we proven here? What have we proven? Validity or invalidity? If you said valid, you'd be right. Why? We were unable to make a row such that all the premises were true and the conclusion false. In other words, there is no possible world where the premises are true, the conclusion false. We've just guaranteed this argument. It is valid. All right. I would do as many exercises as you can. We've only done a few. I've only done a few right here. Try to do as many exercises from the book as you can. There's a number there, and then look at the answers online. They're all online. All right. Hopefully, you're staying healthy, getting through this week, and more videos to come. This is, I think, I've basically covered truth tables. Next subject will be Carroll diagrams. Something new for a lot of logic students. You might have done Venn diagrams before, but now we're going to do Carroll diagrams. So that'll be our next main subject, so be on the lookout for those videos. All right, have a good weekend. Stay healthy, stay logical. All right, I'll see you later.